Now we will start some of the fundamentals which is very useful in kinetics. So first start with the momentum. So momentum, it's a physical quantity which is very useful in kinematics, and momentum is nothing but product of mass and velocity. So momentum is nothing but product of mass and velocity. So we can write momentum equals to mass into velocity. So if we see the formula for momentum, that is nothing but mass into velocity. And I am just giving the one example. Suppose we have two balls, one is made up of rubber and second one is made up of iron, and both are having the same volume and both are moving with the same velocity, but the momentum of the iron ball will be greater than moment of rubber ball, because the mass of the iron ball will be more than mass of the rubber ball. So we can say that momentum, it's not only depending on the velocity, it will also depend on the mass. So for seeing the momentum, we have to see both mass and velocity. So SI unit of momentum, SI unit of momentum is kilogram meter per second, and CGS unit of momentum is gram centimeter per second. So it is about momentum. So let's take the Newton's second law of motion. Newton's second law of motion. So according to the Newton's second law of motion, force is directly proportional to rate of change of momentum. So according to the Newton's second law of motion, force is directly proportional to rate of change of momentum. Suppose we have a block in which we are applying some force F, and due to this force, initial velocity is u, and it is converting into final velocity v. So now we can write initial momentum equals to mass into velocity, and let's take mass of the block is m. So initial momentum mass into initial velocity, that is mu. Similarly, I can write final momentum. Final momentum will be mass into velocity, and here we have to consider final velocity, that is nothing but v. So mv will be the final momentum. So change in momentum. Remember one thing, whenever we are taking the change in any vector quantity, so we have to take final minus initial. So final momentum minus initial momentum. So we are having mv minus mu. Now rate of change of momentum, it is with respect to time. So that is mv minus mu by time. So now according to the Newton's second law of motion, F is directly proportional to rate of change of momentum. So we can write F is directly proportional to, taking m common, v minus u by t, and here v minus u by t is nothing but acceleration, because we know acceleration is rate of change of velocity with respect to time, and proportionality sign, some ma. If we remove the proportionality sign, constant will come, and here the constant value is 1. So F equals to ma. So this is nothing but Newton's second law of motion, which says F is nothing but product of mass. So again, if I write the Newton's second law of motion in terms of momentum, F equals to m v minus mu by t. So now I can write F into t mv minus mu. So now I am defining the new term impulse. Impulse is product of force and time. So here I can write impulse equals to force into time, and it is nothing but mv minus mu. So I can write here mv minus mu. This is nothing but change in momentum. So by this way we can define the impulse, that is nothing but force, product of force and time, that is force into time, and it is nothing but change in momentum. So where large amount of force is applied for a short interval of time, then we will consider the impulse. So there are so many examples which based on the impulse, like uh, sudden jerk. Suppose we are moving in a vehicle, and due to the application of brake there is a sudden jerk on the body. What does it means uh, force is applied for a short interval of time. So we can say that here impulse will come into the picture, because a force is applied for a small interval of time. Similarly, if we go for any sudden impact, like in impact testing or some kinds of sudden impacts are there, now and then in these things also we will use the term impulse, because here also a force will apply for a uh, short interval of time. Or we can say that whenever the force is applied for a short interval of time, then the impact will be more. So in that kind of scenario, we will think about the impulse, means we will think about force as well as the time. Now we will see the conservation of linear momentum. So according to the conservation of linear momentum, if net force acting on a system is zero, then momentum of the system will remain conserved. I will again repeat the law of conservation of linear momentum. If net force acting on a system is zero, then momentum of the system will remain conserved. So let's take an example of collision. So collision of elastic bodies, suppose. Elastic bodies. So suppose there are two bodies having mass m1 and m2. The initial velocity means velocity before collision of m1 is u1, and for m2 mass is u2, and the direction of the velocity is shown by the arrow. And after collision, the velocity of m1 will become v1 and m2 become vt. So this is the thing before collision, and this one is the thing after collision. So we will consider this situation in under the conservation of linear momentum, because here the net force acting on a system is zero. So according to the law of conservation of linear momentum, momentum of the system will remain conserved. It means momentum of system before collision, momentum of system before collision, before collision will be equals to momentum of system after collision, because it is conserved. Before collision in system means we are having two masses m1 and m2. So momentum of system before collision, that is m1 u1, because we know momentum is the product of mass and velocity. m2 u2 equals to, after collision velocity is v1 v2, so momentum of the system is m1 v1 plus m2. So with the help of law of conservation of momentum, we can write this equation. Similarly, the law of conservation of momentum, it is applicable for angular momentum also. So we have to take the proper analogy. Like there is a linear momentum in rectilinear motion. Similarly, in rotatory motion, there will be angular momentum. So we can define the law of conservation of angular momentum also by the same way. Means in place of force, we have to say torque, and in place of linear momentum, we have to say angular momentum. So we can define the law of conservation of angular momentum easily. So the law of conservation of angular momentum, it defines if net torque acting on a system is zero, then angular momentum of the system will remain conserved. So by this way also we can define the conservation of angular momentum. Now talk about conservation of angular momentum. So according to conservation of angular momentum, if net torque acting on a system is zero, then angular momentum of system remains conserved. I will again repeat the law of conservation of angular momentum. If net torque acting on a system is zero, then angular momentum of system remains conserved. So we can write the equation for conservation of angular momentum. Suppose initial angular velocity of mass m1 is omega 1. Initial angular velocity of mass m2 is omega 2. Similarly, final angular velocity of mass m1 is suppose omega 1 dash. Final angular velocity of mass m2 is omega 2 dash. And suppose moment of inertia of mass m1 is I1. Moment of inertia of mass m2 is I2. So now we can easily write the law of conservation of angular momentum. It's nothing but I1 omega. We have to take initial angular momentum, that is nothing but moment of inertia into angular velocity. Similarly, we have already find for linear momentum, that is mass into velocity. But the analogy between the rectilinear and rotatory motion is that in place of mass we have to take moment of inertia, in place of linear velocity, we need to take angular velocity. So that's why the expression is coming I1 omega 1. Similarly, for the mass 2, I2 omega 2. And it will conserve, so final will be I1 omega 1 dash plus I2 omega 2. So by this way, we can write the equation for law of conservation of angular momentum. Now let's take a term which is very important in collision of elastic body, that is coefficient of restitution. As I said, it is very important in collision of elastic body. Important in collision of elastic bodies. So the coefficient of restitution, it is nothing but it is the ratio of velocity of separation to the velocity of approach. So the coefficient of restitution is nothing but the ratio of velocity of separation to the velocity of approach. It is denoted by E. So now we have to understand what is the velocity of separation and what is the velocity of approach. So let's take two elastic bodies M1 and M2. Here velocity is U1 and U2 before collision, and after collision the velocity of M1 and M2 will be V1 and V2 respectively. This is before collision and this one is after collision. So now we see the velocity of approach. So it is now we have to define the velocity of approach. So velocity of approach will be u1 minus u2, and velocity of separation will be v2 minus v. So we can easily define coefficient of restitution. It is nothing but velocity of separation divided by velocity of approach. So we can define v2 minus v1 divided by v1 minus q. So this one is the desired expression E, that is v2 minus v1 divided by u1 minus u2. Now we will define some of the terms related to kinetics. First, work. So whenever if a force is applied on a body, if the force is applied on a body and body will move in a direction of force, then we will say work done on a body by force. So I will again repeat what is force. Suppose if we are applying a force on a body and the body will move in the direction of force, then we can say that work done on a body by the force. Let's take a simple example. Here I am having a block having mass m and I am applying a horizontal force F, and due to this horizontal force F, the block is displaced by distance ds, the direction of force, So now we can calculate the work done. It's nothing but force into displacement. Remember one thing, we have to see the force and displacement in a particular direction. So here I am having force and displacement in the direction of force is ds. So Fds will be the required force. So work done is generally denoted by W. So unit of work in SI system is joule. Similarly, unit of work in CGS system is earth. So these are the most useful units of work in SI and CGS system. So now talk about energy. Energy is nothing but capacity to work is called energy. So there will be a lot of energy like potential energy, kinetic energy, nuclear energy, heat energy, electric energy, chemical energy. So there are various kinds of energy, but in engineering mechanics we are interested in mechanical energy. We are interested in mechanical energy. So in mechanical energy we are having potential energy and we are having kinetic energy. So let's talk about potential energy. Potential energy. So potential energy, it is the energy, due to position of body with respect to earth. Means it is the energy due to the position of body with respect to earth. Suppose this is the earth surface and we are having a body of mass m at a distance of h from the earth. So potential energy, we can write easily, potential energy will be mgh. Means potential energy is depending on the position of the body with respect to earth. If suppose h will increase, then definitely potential energy will also increase. Or in other words, if we move upwards from the surface of the earth, then potential energy of the body will increase. Now let's talk about kinetic energy. So kinetic energy, it is energy due to motion of a body. Energy due to motion of a body. Suppose a body having a mass m is moving with velocity v. So we can say that it is having kinetic energy, and this kinetic energy can be calculated by this formula, that is 1 by 2 mv square. So the kinetic energy is nothing but 1 by 2 mv square, and it is the energy due to motion of the body. So the kinetic energy will depend upon mass of the body as well as the velocity of the body. So now let's talk about relation between work done and kinetic energy. So I am briefly writing the relation between work done and kinetic energy. Work done is nothing but change in kinetic energy. change in kinetic energy. So suppose a body M is having initial velocity and by doing some work the velocity is v. So now in that process work done we can calculate with the help of change in kinetic energy, that is final kinetic energy minus initial kinetic energy. So work done, that is W, final kinetic energy is 1 by 2 m, final velocity, that is v, so v square, minus 1 by 2 m, initial velocity is v, so v square. So work done will be 1 by 2 mv square minus 1 by 2 m v square. Now take the law of conservation of energy. Law of conservation of energy. So according to the law of conservation of energy, for a conservative system, conservative system means there will be no losses of energy. For a conservative system, energy will remain conserved. It means we cannot create the energy, not destroy the energy, but we can convert one form of energy into another form of energy. The meaning of this statement is that means we can change kinetic energy into potential energy or potential energy into kinetic energy, but the summation of all energy will remain same if we are considering the conservative system. So now let's talk about the last terminology, that is power. Power is nothing but rate of doing work. Rate of doing work is called power. Power. So mathematically for power we can write power denoted by P, work done divided by time. So it is work by time, that is nothing but rate of doing work. And SI unit of power is watt. It is nothing but joule per second. So the SI unit of power we can say that watt or joule per second. Sometimes the people are also using different units of power, that is horsepower, kilowatt. They are also using to specify power.